In this module, we will be studying about the position and electronic configuration of D-block elements. D-block elements is the collective name for the groups 3 to 12, in which the d orbitals are progressively filled in each of the 4 long periods. As the D-block elements lie between the S and P block elements, they are also referred to as the transition elements. The F block elements, on the other hand, include the 4F and 5F series of elements, in which the 4F and 5F orbitals are progressively filled. They are often referred to as the inner transition metals because they involve the filling of the inner 4F or 5F subshells. There are mainly 3 series of transition elements. They are the 3D series, the 4D series, and the 5D series. The 4th series, the 6th D series, which begins with actinium, is still incomplete. The first transition series includes the elements from scandium to zinc. The second transition series includes the elements from titanium to cadmium, while the third transition series includes the elements from lanthanum to mercury. By definition, transition elements are those that have incompletely filled d orbitals, either in their elemental state or in any one of their chemically significant oxidation states. Thus, the elements zinc, cadmium, and mercury, which have D10 configuration both in their elemental and their stable oxidation states, are not considered transition elements. The general electronic configuration of these elements is N-1, D1 to 10 Ns, 1 to 2. This generalization has several exceptions, because the energy difference between the Ns and N-1d orbitals is less, and the transition of electrons between Ns and N-1d takes place readily. Furthermore, atoms of the d block elements try to fill their available d orbitals either partially with 5 electrons or completely with 10 electrons whenever possible. This is due to the fact that half-filled or completely filled orbitals impart greater stability to an atom because of the greater exchange energy. A consequence of this factor can be seen in the electronic configurations of chromium and copper in the 3D series. Chromium, for example, has a configuration of 3D5 4s1 instead of the expected 3D4 4s2. Copper, on the other hand, has an electronic configuration of 3D10 4s1 instead of 3D9 4s2. The properties of transition elements depend largely on their electronic configurations. Thus, with partly filled d orbitals, these elements exhibit certain characteristic properties, like display of a variety of oxidation states, catalytic properties, alloy forming ability, complex forming ability, formation of colored hydrated ions and salts, and para- and ferromagnetic properties. The precious metals like gold, platinum, and silver, and industrially important metals like iron, copper, and titanium form part of the transition elements. In this module, we will be studying about the physical properties of D block elements. The electronic configurations of the D block elements differ only in the number of electrons in the d orbitals of the penultimate shell, while the number of electrons in the valence shell remain the same. Thus, they have many physical and chemical properties in common. Nearly all the elements exhibit typical metallic properties. First, let us look at the metallic character. As the number of valence electrons in these elements is very small, all of them are metals. They are good conductors of heat and electricity. They exhibit metallic luster and are hard. They are malleable and ductile. They form alloys with other metals. They have one or more typical metal lattice structures as shown here. Like barium and magnesium, with which they are isostructural, their structures deviate from perfect hexagonal close packing by elongation along the six-fold axis. Mercury is a shiny liquid at ordinary temperature. Let us now look at the melting and boiling point of elements. The melting and boiling points of the transitional elements are generally high. The melting points of 3D, 4D, and 5D transition metals are depicted in the figure here. As you can see in any series, with the exception of anomalous values of manganese and technetium, the melting points first increase to a maximum at 5D configuration and then gradually decrease towards the end of the period. The high melting points of these elements are attributed to the participation of a greater number of electrons from n-1d orbitals in addition to the ns electrons in the inner atomic metallic bonding. Now, let us look at the atomization enthalpies of these elements. These elements have high enthalpies of atomization. The trends in the enthalpies of atomization of these elements are shown in this graph. From the graph, you can see that they exhibit maxima at about the middle of each series. The maxima in each series indicates that interatomic interactions are stronger in half-field d orbitals. It means that the greater the number of unpaired electrons, the stronger are the interatomic interactions and the stronger is the bonding between atoms. Consequently, the higher are the enthalpies of atomization. Enthalpy of atomization is an important factor in determining the standard electrode potential of a metal. Hence, metals with high standard electrode potential tend to be noble in their reactions. For example, copper, due to its high enthalpy of atomization, exhibits noble character. You will also note from the graph that the metals of the second and third transition series have greater enthalpies of atomization than the corresponding elements of the first series. This factor accounts for the occurrence of frequent metal-metal bonding in compounds of heavy transition metals. Let us study about the variation in atomic and ionic sizes of d block elements. The atomic radii of elements in the 3D series are given in the table. Here you can see that the atomic radii of the elements show a progressive decrease in radius with an increase in atomic number. This is due to the fact that an increase in the nuclear charge tends to attract the electron cloud inwards. You already know that d electrons offer poor shielding effect. Hence, the nuclear charge attracts all the electrons more strongly, resulting in a contraction in size. However, the variation within a series is quite small. The same trend is observed in the ionic radii of a given series. The atomic radii of the 3D, 4D, and 5D series of elements are given in the form of curves for comparison. You can see that although the atomic radii increase from 3D to 4D, the atomic radii of the 4D and 5D transition series are very close. This is due to the fact that 4f subshells fill up before the 5d orbitals, which results in a regular decrease in atomic radii. This steady decrease is called lanthanoid contraction. The consequence of lanthanoid contraction is that the radii of the second and third transition series are similar. For example, zirconium and hafnium, niobium and tentaclum, molybdenum and tungsten, technetium and rhenium have close atomic radii and therefore have very similar physical and chemical properties. Like in any transition series, the imperfect shielding of one electron by another in the same subshell is responsible for lanthanoid contraction. However, the shielding effect of one 4f electron by another in the same subshell is less than that of one d electron by another because of the diffused shape of the f subshell. Thus, with an increase in the nuclear charge at each step, there is no comparable increase in the mutual shielding effect of 4f electrons. As a result, the electrons in the outermost shell experience increasing nuclear attraction from the growing nucleus. Consequently, there is a fairly regular decrease in the size of the entire 4Fn orbitals. A decrease in the metallic radius, along with an increase in the atomic mass, results in a general increase in the density of these elements. Thus, there is a significant increase in the density from titanium to copper. D block oxidation states. In this module, we will be studying about the oxidation states of D block elements. One of the most striking features of the transitional elements is their ability to exhibit several oxidation states in their compounds. This unique ability is due to the small difference in energy between the Ns and N-1d orbitals. Because of this, in addition to Ns electrons, N-1d electrons also participate in bonding. Here is the list of common oxidation states exhibited by the first row transition elements. It is important to note that the oxidation states shown in brackets correspond to unstable oxidation state. Some points may be noted from the table, except for scandium and zinc. All the other elements show more than one oxidation state. Scandium, due to the availability of very few electrons for bonding, does not show variable oxidation states. On the other hand, zinc, due to the presence of too many d electrons, has fewer orbitals available for bonding and thus does not exhibit variable oxidation state. The elements from titanium to zinc, with the exception of copper, show a minimum oxidation state of +2. Copper shows a minimum oxidation state of +1. The maximum oxidation state is given by the sum of the s and d electrons for the first 5 elements. For example, scandium, titanium, vanadium, chromium, and manganese exhibit maximum oxidation state of +3, +4, +5, +6, and +7 in the form of their oxides, oxyanions, and oxycations as shown here. The maximum oxidation states of the elements after manganese are not at all related to their electronic configurations. For example, cobalt shows only +2 and +3 stable oxidation states. The relative stabilities of various oxidation states of 3D series elements can be correlated with the extra stability of D30, D35, and D310 configurations to some extent. Thus, a titanium A4+ ion with D30 configuration is more stable than a titanium 3+ ion with 3D1 configuration. Similarly, a manganese 2+ ion with 3D5 configuration is more stable than a manganese 4 plus ion with 3D3 configuration. The transitional elements exhibit oxidation states that differ from each other only by 1 unit. This is in marked contrast to the S-block elements, which exhibit only the group valency, and the P-block elements, which exhibit either the maximum group valency or the valency less by 2 units. For example, manganese exhibits all the oxidation states from +2 to +7, which differ from each other by unity. On the other hand, tin and lead, which belong to group 14, exhibit oxidation states of 2 and 4. We know that in P-block elements, lower oxidation states are favored by heavier oxidation elements because of the inert pair effect. However, in D-block elements, higher oxidation states are more stable for heavier elements. For example, for group 6, molybdenum 6 and tungsten 6 in the form of their oxyanions are found to be more stable than a dichromate ion, in which chromium is in its highest oxidation state of 6. Thus, a dichromate ion acts as a strong oxidization agent in an acidic medium, while the oxyanions of molybdenum and tungsten do not. Some transition metals also show zero oxidation states in complexes like carbonyls, where ligand acts as a pi acceptor. Nickel tetracarbonyl, iron pentacarbonyl shown here are 2 examples of a transition metal in zero oxidation state. In the lower oxidizing states, these elements form ionic compounds. For example, manganese 2 oxide and chromium 2 oxide are ionic in nature. The tendency to form ionic compounds decreases with an increase in the oxidation number of the metal. Higher oxidation states give rise to covalent compounds. For example, manganese 2 oxide is ionic. Manganese 4 oxide is intermediate between ionic and covalent, and manganese 7 oxide is purely covalent. As the oxidation state of the transition metal increases, the charge density of the metal also increases. This results in the increase of polonization of the anion charged cloud by the metals, and hence the covalent character increases. The acidic nature of the oxides increases with an increase in the oxidation state of the transition element. For example, manganese 2 oxide is basic, manganese 4 oxide is amphoteric, while manganese 7 oxide is acidic in nature. Similarly, chromium 2 oxide is basic, chromium 3 oxide is amphoteric, and chromium 6 oxide is acidic. A gradual change in the nature of the oxide from basic to amphoteric can be clearly seen in vanadium. Vanadium 3 oxide is basic, while vanadium 4 oxide is less basic. On the other hand, vanadium 5 oxide is amphoteric with more acidic properties. Vanadium 5 oxide reacts with alkalis to give orthovalidate ions and with acids to give dioxyvanadium 5 ions. In higher oxides, the acidic character is predominant. Thus, manganese 7 oxide gives permanganate acid, while chromium 6 oxide gives chromic acid and dichromic acid. In this module, we will be studying about the standard reduction potential trends and stability of higher oxidation states of D block elements. Here we can see the observed and calculated values of the standard reduction potentials for the reduction of N+2 ions to their respective metals. It also shows that the thermochemical data related to the transformation of the solid metal atoms to N2 plus ions in solution. The calculated values of the potentials are those based on the standard enthalpies of formation of the +2 ions in an aqueous solution. The blocks of the experimental and calculated values of the reduction potentials are shown in the figure. The curve in red corresponds to the observed values, while one in black corresponds to the calculated values. The plots indicate that the experimental and calculated values are in close agreement with each other. The M+2 to N reduction potentials have enthalpic contributions from the terms in the equation shown here. The equation indicates that the magnitude of the reduction potential is governed by the values of three relatively large terms. The negative enthalpy of hydration M2 plus 840. The sum of the first and second ionization enthalpies and the smaller term enthalpy of atomization. The interplay between these three terms decides the value of the reduction potential. The irregularity in the variation of electrode potentials is due to the irregular variation of the ionization enthalpies and also the hydration energies of the divalent ions of these elements. All those elements with negative reduction potentials act as strong reducing agents and liberate hydrogen from dilute acids. For example, titanium 2+, vanadium 2+, and chromium 2+ ions act as strong reducing agents and liberate hydrogen from a dilute acid as shown in the equations here. On the other hand, copper with a positive reduction potential does not liberate hydrogen from dilute acids. Thus, copper is inert towards non-oxidizing acids such as HCl, but reacts with oxidizing acids such as nitric acid and hot concentrated sulfuric acid as shown here. The reason for this behavior is the high energy needed to transform solid copper to gaseous cupric ion, which is not exceeded by the hydration enthalpy of the ion. The general increase in the ionization energies sum is dominant in deciding the trend towards the less negative values of the n+2m reduction potentials. It is interesting to note that the values of the reduction potentials for manganese, nickel, and zinc are more negative than expected. The electrode potential values of manganese and zinc can be explained on the basis of the stability of the half-filled D subshell in Mn2 plus and the completely filled D10 configuration in zinc 2 plus ion. The stability is due to the maximization of the extreme energies between electrons of like spin. The electrode potential for nickel is related to the highest negative hydration enthalpy corresponding to its smaller radius. Now, let us look at the trends in the standard electrode potentials of M+3 ions to N+2 ions. Not all the first row transition elements have the same pairs of stable oxidation states. The elements from vanadium to cobalt are chosen because they all have +2 and +3 state, for which reliable experimental data are available. The observed electrode potentials for these elements are shown in the table. The lower value for vanadium is due to the stability of V2+, as it has a half-filled T2G level. Manganese has a higher electrode potential value than chromium and iron because of its very high third ionization energy, which is again due to the stability of the half-filled D5 configuration. The higher values from manganese and cobalt show that the other strongest oxidizing agents are in aqueous solutions. The comparatively low value for iron shows that the reduction of ferric iron to ferrous iron is less favorable, since ferric iron is extra stable due to the half-filled D5 configuration. Let's now look at the trends in stability of the higher oxidation states of these elements. The table here lists the stable halides of the 3D series of the transition elements. As can be seen from the table, titanium tetrahalides, vanadium pentafluoride, and chromium hexafluoride have the highest oxidation numbers. The highest oxidation state, +7 for manganese, is not seen in simple halides, but MnO3F is known. Beyond manganese, no metal has a trihalide, with the exception of cobalt trifluoride and the trifluoride, trichlorides and tribromides of iron. Fluorine stabilizes higher oxidation states, either because of its higher lattice energy, as in the case of cobalt trifluoride, or higher bond enthalpy, as in case of vanadium pentafluoride or chromium hexafluoride. Thus, vanadium pentafluoride is stable, while the other halides undergo hydrolysis to give oxohalides of the type VOX3. Fluorides are unstable in their lower oxidation states, and therefore chlorides, bromides, and iodides exist in +2 oxidation state, while fluorides do not. Copper, in +2 oxidation state, forms all the halides, except iodides, because cupric iron oxidizes iodide to iodine. Copper plus 1 compounds, being unstable, react with solutions and undergo disproportionation to give stable cupric ion and copper. According to the equations shown here, the stability of Cu plus 2 ions is due to the higher negative hydration enthalpy of cupric ion than cuprous ion, which more than compensates for the second ionization enthalpy of copper. Now, let's look at the higher oxidation states in oxides. Here you can see the oxides of the 3D series of elements. The highest oxidation number in an oxide coincides with the group number and is obtained from scandium 3 oxide to manganese 7 oxide. No higher oxides are seen beyond manganese. For example, the only stable higher oxide formed by iron is iron 3 oxide. Although iron forms ferrate and alkaline media in which iron is in +6 oxidation state, it readily decomposes into iron 3 oxide and oxygen. Apart from oxides, oxygen also stabilizes higher oxidation states in the form of oxocations. For example, vanadium 5 is stabilized as dioxovanadium 5 ion, vanadium 4 as oxovanadium 4 ion, and titanium 4 as oxotitanium 4 ion. Oxygen exceeds fluorine in its ability to stabilize higher oxidation states. Thus, the highest manganese fluoride is manganese tetrafluoride, while the highest oxide is manganese heptoxide. The ability of oxygen to form multiple bonds with metal atoms is responsible for its superiority over fluorine in stabilizing higher oxidation states. This ability can be clearly seen in the covalent oxide, manganese heptoxide. In this compound, each manganese atom is surrounded by 3 doubly bonded oxygen atoms, including an MnO-Mn bridge. Similarly, oxygen also forms double bonds in the tetrahedral MO4N- ions, known for vanadium 5, chromium 6, manganese 5, manganese 6, and manganese 7 ions. In this module, we will be studying about the electronic configuration, atomic and ionic size, and oxidation states of F-block lanthanoids. The two rows of elements at the bottom of the periodic table constitute the F-block elements. These include the 14 elements from cerium to lutetium called the lanthanoids and the 14 elements from thorium to lawrencium called the actinoids. While lanthanoids are characterized by the filling up of the antipenultimate 4F energy level, actinoids are characterized by the filling up of 5F energy level. These two series of elements are therefore called the inner transition elements. Since the D-block element lanthanum closely resembles the lanthanoids, it is usually included in any discussion of lanthanoids. Since lanthanoids effectively have only one stable oxidation state, +3, they resemble each other more closely than do a horizontal row of the transition elements. The electronic configuration of the lanthanoids is as shown in the table. Lanthanum, the D-block element preceding this series, has the electronic configuration of xenon core 5D1, 6s2. We might expect that the 14 elements from cerium to lutetium would be formed by adding 1, 2, 3, up to 14 electrons to the 4F level. However, for most of the elements, except cerium, gadolinium, and lutetium, it is energetically favorable to move the single 5D electron to the 4F level. The reason why gadolinium has a 5D1 arrangement is that this leaves a half-filled 4F subshell, which gives greater stability. Lutetium has a 5D1 arrangement because the F subshell is already full. The lanthanoids are characterized by the uniform +3 oxidation state shown by all the metals. Let us now look at the atomic and ionic radii of these elements. The atomic and ionic radii are as shown here. You can see that the atomic radii exhibit a smooth trend across the series, with the exception of the element europium. Europium, because of its crystal structure, has abnormal atomic radius. The ionic radii of the trivalent lanthanoid ions, in contrast, exhibit a smooth decrease. In lanthanoids and their trivalent ions, the effective nuclear charge experienced by the outer electrons increases with an increase in the atomic number due to the poor shielding of the F electrons. Hence, a regular decrease in the atomic radius is observed with an increase in the atomic number. This steady decrease in size of the atom or ion among the lanthanoids is known as lanthanoid contraction. Because of lanthanoid contraction, the sizes of the third row of the transition elements are very similar to those of the second row. Thus, the second and third rows of the transition elements resemble each other more closely than do the first and second rows. Thus, pairs of elements such as zirconium and hafnium, niobium and tantalum, and molybdenum and tungsten are almost identical in size. The close similarity of properties in such a pair makes chemical separation very difficult. Now, let us look at the oxidation states of these elements. The sum of the first three ionization energies for each element is given in the table. The values are low, Thus, the oxidation state of +3 is ionic, and the trivalent lanthanoid ion dominates the chemistry of these elements. The divalent and tetravalent lanthanoid ions that do occur are always less stable than divalent lanthanoid ions. The oxidation numbers of +2 and +4 do occur, particularly when they lead to a noble gas configuration, a half-filled F subshell, a completely filled F subshell. An example of the first class is cerium 4+ ion. Although cerium 4+ is favored by its noble gas configuration, it is a strong oxidizing agent, which is evident by the standard reduction potential value of the cerium +4, cerium +3 couple. Therefore, it reverts to the stable +3 oxidation state. In addition to cerium, neodymium, promethium, terbium, and dysprosium also exhibit +4 oxidation state in their oxides. The best examples of the second case are europium +2 and terbium 4+. However, europium +2, being a strong reducing agent, changes to +3 oxidation state. Cymerium, like europium, also exhibits both +2 and +3 oxidation states. Terbium +4, on the other hand, acts as an oxidant and gets itself reduced to +3 state. A terbium 2+ stands as an example of the third case. A terbium 2+ ion acts as a reducing agent and changes to +3 state. In this module, we will study about the general characteristics and uses of lanthanoids. The important physical properties of lanthanoids are: all lanthanoids are soft and silvery white metals. The hardness of these metals increases with an increase in the atomic number. They are electropositive and therefore very reactive. They rapidly tarnish in air due to the formation of an oxide coating on their surface. They are good conductors of heat and electricity. Their physical constants like melting point and density change gradually, except in the case of europium, ytterbium, samarium, and thulium. Many of the trivalent lanthanoid ions are colored, both in their crystalline state and in aqueous solutions. The color of these ions is directly related to the number of unpaired electrons in the 4f subshell. The absorption spectra of the compounds of trivalent lanthanoid ions show a very sharp line band in the UV visible or near infrared region. These bands are due to internal electron transitions in partly filled 4f shell and are called F to F transitions. Lanthanoid ions that have empty F orbitals, like trivalent lanthanum, half-filled F orbitals, like trivalent gadolinium, or completely filled 4f orbitals, like trivalent lutetium, are colorless. Due to the presence of unpaired electrons in the 4f orbitals, all lanthanoid ions show paramagnetic behavior, with the exceptions of trivalent lanthanum and tetravalent cerium with F0 configuration, and divalent ytterbium and trivalent lutetium with F14 configuration. Paramagnetism is the maximum in dysprosium. The value of the first ionization energy of the lanthanoids is about 600 kilojoules per mole, and of the second ionization energy is about 1200 kilojoules per mole. These values are comparable with the values of the ionization energies of the alkaline earth metals, particularly calcium. The detailed study of the third ionization energy shows the extra stability associated with empty, half-filled, and completely filled orbitals of the F level. This is reflected by the abnormally low value of the third ionization enthalpies of lanthanum, gadolinium, and lutetium. Now, let us look at the chemical reactivity of these elements. The first few members of the lanthanoids are quite reactive and show chemical behavior similar to that of calcium. However, with an increase in the atomic number, they behave more like aluminium. The standard electrode potentials of the Lm+3 Lm couple indicate that all the lanthanoids are more reactive than aluminium. Let us now look at some important reactions of these elements. These metals combine with hydrogen when heated gently in the gas and form hydrides of the type LmH2 and LmH3. On being heated, these elements combine directly with nonmetals and form carbides with carbon, nitrides with nitrogen, sulfides with sulfur, and halides with halogens. They liberate hydrogen from dilute acids. They burn in oxygen to form oxides of the type Lm2O3. They react slowly with cold water, but more rapidly with hot water, and liberate hydrogen gas. The lanthanoid oxides and hydroxides are basic in nature. Like alkaline earth metal oxides and hydroxides. Let us now look at the uses of lanthanoids. Lanthanoids are widely used for the production of alloy steels, for pipes and plates. A well-known alloy mish metal, which consists of 95% of a lanthanoid metal, 5% of iron, and traces of sulfur, carbon, calcium, and aluminium, is used in a magnesium-based alloy to produce bullets, shells, and lighter flint. Mixed oxides of lanthanoids are used as catalysts in petroleum cracking. Some individual lanthanoid oxides, such as europium oxide and ytterbium oxide, are used to produce the red colors on television screens. The oxides of praseodymium and neodymium are used in glass, such as in television screen, to reduce glare. In this module, we will be studying about the electronic configuration, atomic and ionic size, and oxidation states of F-block actinoids. The 14 elements from thorium to lawrencium, in which the differentiating electron enters the 5f orbital, are called the actinoids. Only the first three elements, namely thorium, protactinium, and uranium, occur in nature. The other elements are made artificially by nuclear bombardment. All the actinoid elements are radioactive. The first few members have relatively long half-lives. However, the remaining members have half-lives ranging from a few days to a few minutes. Let's first look at the electronic configuration of these elements. The electronic configuration of actinoids is as shown in the table. Since the difference in energy between the 5f and 6d orbitals is small for the first four elements, thorium, protactinium, uranium, and neptunium, the electrons in these elements and their ions may occupy the 5f or the 6d levels, or sometimes both. However, note that the filling of the f orbital starts only at protactinium and not at thorium. Later in the actinoid series, the 5f orbitals do become appreciably lower in energy. Thus, from plutonium onwards, the 5f shells fill in a regular way, and the elements become very similar. The irregularities in the configurations at curium and lawrencium are related to the stabilities associated with the half-filled and completely filled configurations. Since the 5f orbitals are not as deeply buried as 4f orbitals, the 5f electrons can participate in bonding to a greater extent. This explains the higher oxidation states shown by the earlier actinoid elements. Now, let's look at the atomic and ionic radii of these elements. The atomic and ionic radii of the tripositive and tetrapositive actinoid ions are given in the table. As you can see, there is a steady decrease in the ionic sizes of the tripositive and tetrapositive ions. This may be referred to as actinoid contraction. Due to the poor shielding by the 5f electrons, the contraction is greater from one element to another in the series. Let us now discuss about the oxidation state of these elements. Unlike lanthanoids, actinoids show a variety of oxidation states. This is attributed to the small energy difference between the 5f, 6d, and 7s levels. The oxidation states of these elements are given in the table. You can see that +3 is the common oxidation state of actinoids. The maximum oxidation state first increases up to the middle of the series and then decreases. That is, it increases from +4 for thorium to +5, +6 and +7 for protactinium, uranium, neptunium, and plutonium, but decreases in the succeeding elements. Actinoids, like lanthanoids, have more compounds on the +3 state than in the +4 state. However, +3 and +4 ions in actinoids tend to hydrolyze while lanthanoid ions do not.